We're going to talk about trig equations again today. Jumping right into it. Um, what is the value of sine of pi over 2? Well, we know from our unit circle it lies right on our our y-axis here, and the sine value is just 1. So sine of 5 or pi over 2 is equal to 1. Now, we know from before that we can go through many revolutions of the unit circle. So right now, let's say we went through one revolution, and keep in mind that one revolution is 2 pi. What would be this value then now, right? So what would this angle be if I went all the way past 2 pi and then added an extra pi over 2 onto it? This would make it so that way we have sine of 5 pi over 2, right? So pi over 2 plus 2 extra pi's. But the value is going to stay the same here for 5 pi over 2. It's still equal to 1. If I do another revolution here, so this time going past this section, and if you wanted to think of it this way, now we're going to talk about 4 pi. So a second revolution would be 4 pi, and adding a little bit on top of 4 pi would be an extra pi over 2. That would make it so I have sine of 9 pi over 2. And that's still equal to 1, right? Because this value here isn't going to change. So our values that occur on the outside of the unit circle are always going to be staying the same. What does change is the angle on the inside. Now this can go on forever and ever and ever and ever. The left-hand side here can keep going and going and going. So we could have 13 pi, we could have multiples of that, of pi over 2, 5 pi over 2, 9 pi over 2, 13, 17, 21, so on and so forth. But what's going to stay the same is the value. The values will always stay the same. So what we do in math is, instead of just kind of doing this over and over again, is we change what's called the domain. And the domain for us usually up to this point has been between 0, x has been between 0 and the value of 2 pi, which this translates into being one revolution or one total spin or one total way around the unit circle. So we go from 0 all the way to 2 pi. What we're going to do today is we're going to go between 0 and 4 pi. And so 4 pi is 2 total revolutions. So we'll go one revolution around and then a second one. And you'll see that you're going to have sometimes up to 4 answers here for our values of what our trig equation is equal to. So we'll go to something a little familiar here to start. Let's say that we have 2 sine x is equal to 2 sine x minus 1 is equal to 0. Now we'll quickly tidy this up like we've been doing in class, and we'll say 2 sine x is equal to 1 and sine of x is equal to 1 over 2. What we have to do again, remember our steps from class. Step 1 is figure out where it's positive and negative, and we know that sine is positive in the top 2 quadrants. We look at our special triangles, and we'll say that we have our root 3, 2, and 1. Sine is the ratio where it's opposite over the hypotenuse. So I know that my opposite of 1 here is pi over 6, and my hypotenuse is 2. So my reference is equal to pi over 6. And then step 3 was to sort out what those values are in those quadrants. So I have my ref and my pi minus reference. X, for the sake of this question, could be equal to pi over 6, or it could equal pi minus my reference, which, for the sake of time here, I'm just going to tell you would be 5 pi over 6. So hopefully we're very familiar with getting to this point for x. Let's say now, let's put this on our graph. So this is our value at pi over 6, and this is our value at 5 pi over 6. Let's say now we wanted to change the domain or include a domain that goes from 0, that includes x, and it goes all the way up to 4 pi. This may seem a little different and hard to begin with, but all we have to really do is add 2 pi to every single answer that we've already gotten. So here, what this is really saying is that, okay, we'll go through 1 pi, one revolution will go all the way down to 2 pi. And those are our 2 values if we were to stay in those domains. But here, I'm going to hit this value again. And this would make it so that way I have pi over 6 plus an extra 2 pi. Here, over on this side, it's going to be the same value of 5 pi over 6 plus an extra 2 pi. Now remember, at each of these situations, sine x is still equal to 1/2. It's equal to 1/2 here, it's equal to 1/2 here. Our values on the outside stay the same, but the angles that make those values will change. So if I were to change what my x is equal to down here, I'll include my pi over 6 and my 5 pi over 6. But I also have to include pi over 6 plus 2 pi. Now remember, another way to write 2 pi is 12 pi over 6. So I could write pi over 6 plus 12 pi over 6. And I could also write 5 pi over 6 plus my 12 pi over 6. So these are now, I have 4 answers here. So x, in this case, where 2 sine x minus 1 equals 0, on the domain where x is between 0 and 4 pi, I can have 4 answers where it's equal to pi over 6, 5 pi over 6, 13 pi over 6. I have 13 pi over 6 here. And I could also have 17 pi over 6. All right, so this is where it's a little bit different. So our x values can be all of these, as opposed to originally we just had our values of pi over 6 and 5 pi over 6. How do you know where to stop? Well, the best way that I can explain to do that, and this is what I often do with my when I'm doing these myself, is I change the domain in reference to, or I guess in relation to my reference angle. So pi over 6, I'll translate this 4 pi into multiples of pi over 6, which will be 24 pi over 6. And I'll know when to stop when I break that 24 pi over 6. So if I were to add 2 more pi to 13 pi over 6, that would make it so that way I would get 13 pi plus 12 pi, which would be 25. And that's way too large. It's bigger than my 24 pi over 6. And that's a good way to just know if you're getting all of the answers that you need to. So 4 answers here. None of them are greater than 24 pi over 6. And that's how you know when to stop. Do another one here for good measure. Let's go through a tan example. So tans are just slightly different here. So tan x, we'll move that root 3 to the other side. It's equal to a negative root 3. Now we need to know where is tan positive and negative. We know that tan is negative in the sine and the t, or the tan quadrant. Oops, sorry, that should be a cos quadrant. And so I'll just draw the rest of them out here. We will have negative tans in S and C. If I draw my special triangle that involves the root 3 here, I know that tan is the opposite over the adjacent. So my opposite angle here should be pi over 3. My adjacent is 1. So that means my reference is equal to pi over 3. So now I know what my reference is. I'm going to change my domain to reflect that. So pi over 3, 4 pi in terms of something over 3 will make it so that way I have 12 pi over 3. So I know that if I'm finding any values that break 12 pi over 3, I've gone too far when I'm adding my values here. So again, we still have to go through all these steps. I know that I'm going to live in the pi minus reference and the 2 pi minus reference quadrants. So I could have answers that would look something like 2 pi over 3. 2 pi over 3 would live here, and 5 pi over 3 here. So that would be 2 pi over 3 and 5 pi over 3. Again, though, we have to add some revolutions of pi here. So if you look at the unit circle and we talk about tan, well, I have something like 2 pi over 3 here, and I'll have something like 5 pi over 3 down here. These things are a single revolution of pi away from each other. So they're directly 180 degrees away from each other, or one revolution of pi. So in these cases, with tan, we have to add pi to each value. Now, if I wanted to add pi to this value here, that would be adding 3 pi over 3, and that would give me 5 pi over 3. So these are exactly 1 unit of pi away from each other. I'll add 1 unit of pi to 5 pi over 3 here to include me going all the way around here again, going past my 2 pi. And that'll make it so I have a value of 8 pi over 3. And then if I wanted to add more to see how close I could get to 12 pi over 3, I'm going to make it so that way I get to 11 pi over 3. Now, could I add another another revolution of pi here? No, I could not, because that would make it so that way it's 14 pi over 3, which would totally break my domain, which I cannot do. So these are the values that I'm stuck with for this question here. A couple of takeaways here. When we're dealing with sine x and cos x, and in particular when we're dealing with domains that are greater than 2 pi, we're dealing with 4 pi domains now, we will add 2 pi to each answer that we already have. So we add 2 pi to each answer when solving on 0 to x to 2 pi. So once we solve our answers for the original domain we usually do between 0 and 2 pi, we add 2 pi to each answer. Okay, so if that's a little bit confusing, go back and watch the first example we did to kind of clarify that. And for tan x, we add pi. So here we'll add 2 pi for sine and cos. For tan, we'll add pi to each answer when we originally solve on 0 to x to 2 pi. Okay, so we usually will find the answer on 0 to 2 pi, and then we will add 2 pi to each answer for sine and cos, and we'll add pi only to tan x. What I'm going to get you to do now is take a crack at some of these. So you can take a look at these. I'll post the answers to these onto our portal page, so that way we can get some practice. And again, these things might seem a little bit daunting at first, but the more practice that we can get, the better that we're going to be at these things. So like I said before, we're going to have a little mini assessment in class on Tuesday, and that will require you to solve a couple of things, and a couple of those things will involve solving for domains that are greater than 2 pi. So here, for these examples, it would be fantastic if you can take a stab at solve for x on the domain of 0 to x to 4 pi. All right? So take a look at those during class time today. Like I said, I'll post the answers onto our onto our portal page. And again, email me if you have any questions or concerns, or talk to one of your teachers. Thanks for watching. Have a good night.